Hi, everyone. Hope you had a good week. We continue on with a bit of waves today. And what I want to talk about is what happens when waves reach a boundary. That is, what's a boundary? Anytime it goes from one density to another density. It could go from air to water, from water to air, from a string to something denser than that, that's less mobile, all those kind of situations. So take a look at these kind of situations real quick. One type of boundary you might run into is when a wave, or these are all pulses, run into a boundary here, where in this case, this area right here is more dense. What's going to happen here? Notice that the wave comes in, it hits it, and it bounces back on the opposite side. We say it's inverted. The same thing happens over here. So if you've got an incident pulse, the string here is tied to the pole. It's not free to move. The reflected pulse comes back on the opposite side. As long as there's no dampening, that is any kind of resistance, the reflected pulse should have the same speed because it's in the same medium. It'll have the same wavelength and the same amplitude as the incident pulse because the speed hasn't changed at all. Amplitude doesn't change if there's no friction. So this is the Wave app that's attached or linked to your assignment sheet. And I just want to show you what happens when we send a pulse down this array of masses connected by springs. This is supposed to be a window, so it goes on forever. If you send a pulse down, it just gets smaller and smaller, but goes on forever. Remember also that as you decrease the tension, if you remember the equation, the velocity in a chain like this is proportional to the square root of tension over mu, where mu is the mass per unit length. The velocity becomes a little bit smaller if the tension becomes smaller. Let me reduce it even more, and you end up with really, really slow tensions. And so you're like, okay, that makes sort of sense, but now let's change it a little bit. What if I replace the window with a fixed end? In this case, I've clamped this end down. And let's go ahead and send a wave down it and watch what happens. Wave hits it, bounces back on the opposite side. Both ends here act like fixed points. And so when a wave goes from one media to something that's more dense, in this case, a very hard reflection, it gets inverted at that reflection point. You'll notice the wave gets smaller and smaller because I do have a little bit of dampening turned on. If you turn that off, it would go on forever. So that's what happens if it hits a more dense end, it gets inverted. If it comes as a crest, it bounces back as a trough. If it comes as a trough, it bounces back as a crest as it returns. What happens if you leave it as a loose end? In this case, there's just a little loop of string here wrapped around this vertical pole. And watch what happens now. So the wave comes in and it bounces back on the same side, on this side, because it's free to move. This would be like a wave going from a more dense medium to a less dense medium. And so you end up with a reflection that's on the same side. Again, when it hits this end here, this is considered a fixed end or more dense end. It comes back inverted when it hits this end. Inverted, same side. Inverted, same side. Hope that makes sense. All right, so you've seen what happens there. I'm going to take it a little bit nicer. I wish the app had this option. But if you've got a wave that's going down something that's of less dense medium, in this case, it's a very thin string, and it runs into, let's say, a thicker rope, what happens at the boundary? Well, going from less dense to more dense, we get an inverted pulse reflection at this point. But the transmitted wave, the one that goes through the boundary, stays on the same side. So transmitted pulses going from one medium to another is always on the same side. So you'll notice down here, oh, there's the school bell if you missed it. The interesting thing about this, the speed and wavelength of the reflected pulse remain the same, but the amplitude decreases because part of the energy went through that boundary system. So notice the amplitude gets smaller coming back. It's inverted. The wave speed and amplitude of the transmitted pulse are all smaller than the original one. Why? The speed gets slower. Not all the energy is transferred. And the wavelength gets smaller because the velocity is smaller in the more dense medium, typically, at least for ropes. What happens if you go from more dense to less dense? Well, this is like that string not connected to, or free to move on this side where it's less dense. In that case, the reflected pulse is back on the same side, and the transmitted pulse
also on the same side. So transmitted pulse is always on the same side. But if you're going from more dense to less dense, the reflected pulse is on the same side. The transmitted pulse is larger in amplitude. It's traveling faster, so its wavelength is also is larger as well. In this rather eerie video, you're looking at my reflection, looking through one of the windows in the classroom that goes out to the hallway. Now you're seeing my face reflected off the front of the glass, and you're seeing the plant that's actually out in the hallway. I know it looks a little eerie, but think of now in terms of the waves. Where my face is inside the classroom is surrounded by air. So the light waves that are reflecting off my face travel through air, hit the glass, and then bounce back to the camera that I'm holding in the other hand. What's that doing? Anytime a wave goes from one medium that's of low density to high density, it gets inverted in the reflection. So the transverse light waves the camera's seeing are actually inverted, not that they look any different. And what about the light from the plant in the hallway? Well, yes, part of it reflects off the surface of the glass in the hallway. That does get inverted. But the part that travels through the glass is not inverted. And then when it leaves the glass to come back into the air of the classroom, it's also not inverted. And so you're seeing the plant uninverted transverse light waves. Now, a couple quick things I should explain. You'll see me glancing over because I was holding my phone in one hand. I had to make sure I was still centered on it as I was filming this. But there's another thing I want to talk about. I don't know if you can see this, but there's actually two edges of my face in this video. And I just want to explain why. Here's the glass pane, sort of looking down from above. Here's the hallway. Here's my classroom. And this is where my head was inside the classroom. What was going on here? Some interesting effects. Yes, light could come from my face, bounce off the glass this way, and come to the camera. But some of the light also went through this boundary. Remember, every single time that happens, by the way, yeah, this is inverted, coming back out here. But some of it got transferred through here, and some of it then hit the backside of this glass, which is a boundary from more dense to less dense air, and also reflected back. This would be non-inverted, and so you actually get two images arriving in the camera from slightly different positions, which is why you see two edges of my face. And yes, some of this light also did go through here, so if you're standing in the hallway, you could still see my head. Yeah, this is the glass again, just kind of give perspective. But that's why you're seeing these double images, which is kind of cool. Interference and superposition are kind of cool. What happens when two waves pass through the same medium? What happens? If two waves run into each other, what they do is simply add, and that's called the superposition principle. Superposition, when two waves interfere, the resulting displacement of the medium at any location is the algebraic sum of the displacement of the individual waves at that location. So in this case, you've got this little red wave here and this blue wave here. They're moving towards each other. At the moment they overlap, the resultant wave is this green wave, which is just the algebraic sum of the red and green at every single point along this way. And that's it. That's all that superposition allows. And you might say, whoa, why is this helpful? There's two types of interference. There's constructive interference. That's where the waves add, like you see down here. And there's also destructive interference, where a crest meets a trough. What's so interesting about that? Well, destructive interference is how your noise-canceling headphones work. They literally have a microphone at the outside edge and going through some circuitry that generates an exact waveform of the outside noise, but it's exactly out of phase. So if the outside noise, for example, would look like this, it would generate a wave that looks exactly opposite that in magnitude and everything else, so that the sum of these two at every single point would simply add up to zero. And that's how it cancels the external sound that you're hearing. I didn't quite do this part right, but close, you get the idea. So here's constructive interference. You've got these two waves coming in. They're in phase of each other where this crest meets this crest. I need to change my pen color. What happens then? You end up with a crest here that has twice the amplitude, twice the A of either one of these individual waves as they come together. The crests and the troughs reinforce each other to become twice as large. So again, this is the kind of construction we have. Crest meeting crest, we get twice as big, or trough meeting trough, we get twice as big of a trough. These are for pulses down here. These are continuous waves up here. Here's an animation, and sorry, it's a little bit slow loading in here.
What happens when the two crests pass?
At every single point, they add till they're right on top of each other, and then they pass through each other. They don't bounce off each other.
What happens when the two crests pass? What happens when a crest meets a trough?
And they go straight through each other, but a brief
What
instant
happens when
they
a sine
cancel out.
crest meets a square crest?
Now we're getting to some more unusual waves. A sine wave and a square trough.
What happens when a sine crest meets a square trough? What happens when a sine crest meets a triangle crest?
And yes, you can have a
What
triangle
happens
wave.
when a sine crest meets a triangle trough?
So yeah, you've got seen some pretty strange ones here. I want to show you another quick example. This is a U.S. Navy ship. So in a storm, you've got waves coming from all directions of different amplitudes and wavelengths. In this particular case, this particular wave that's about to go over was super large. It's called a rogue wave. And now what happens here is the bow of the boat actually goes underwater. What you're seeing here is the bridge windows actually under the ocean there for a moment. And the bridge is 3 stories up on top of the Navy ship. Rogue waves have been known to actually capsize boats if they hit them wrong. And it's just the idea that you can have constructive interference between a bunch of different waves. I just want to show you again, sort of in this sort of an analogy. You've got 2 transverse waves up here, and they add together because they're in phase, and you end up with a transverse waves that's twice as large. Here it is represented as a longitudinal wave, as a series of compressions and rarefactions. Think about this as like sound waves moving through air is a good example of a longitudinal wave. What happens if you get 2 of these in phase with each other, where the compressions meet compressions? You end up with larger, more high pressure compressions and lower low pressure rarefactions in between them. You can also have destructive interference. I mentioned this before. In this case, if you've got one wave where the crest here meets a trough here, what happens when you add these 2 waves together? Well, at every single point, algebraically, these add up to 0. And so briefly, if you've got a crest going this way and a trough going this way with the same amplitude, when they're right on top of each other, the moment they're right next to each other, you end up with 0 here, which is a pretty bizarre idea, that waves can actually cancel each other. Everybody always asks me usually at this point, hey, light is a wave. Can I make a flashlight that instead of making things light, make things dark? You've got noise canceling headphones. Could you make a light canceling flashlight? And the answer is, you could, but you'd have to make sure that the photon you were trying to cancel was moving it exactly along the exact same line as the photon that you're producing that was exactly out of phase with it. Would it cancel everything along everywhere, every other angle? The answer is no. So you can't make things disappear. You can't cancel all light. But can you cancel light? Yeah, it turns out. Usually I do this as a demo. You take 2 laser beams, which are nicely monochromatic, single frequency, and you run them off a mirror, and you can have them destructively interfere. Here's destructive interference with, again, sound waves. What happens here? You've got a compressions here, and they're out of phase with the compressions here, where this compression meets up with a rarefaction here, this compression here meets up with a rarefaction here, and you end up with no pressure waves at all over here in the longitudinal wave. And over here, where the 2 transverse waves end up, it just stays at equilibrium. What if the 2 waves are not exactly the same amplitude? Then you don't get complete cancellation, and you'll still end up with whichever one has a larger amplitude, that'll remain over here. It'll be smaller, but it won't completely cancel out. Here's some more. Here's a quick video or screen, actually a bunch of little video clips of two pulses along a real spring. Normally, when you're here, we do this out in the hallway. The two pulses are approaching each other. They're getting really close. And then right here, and I know it's not exactly perfect, they're right on top of each other, and you end up with them basically canceling. And then after that, they keep moving on after that collision. Ooh, brain break. Ooh, yay. For each puzzle below, identify the two missing letters and unscramble letters to form a word. For example, BJM becomes banjo. Ooh. Oh, okay. Two missing letters. First one looks ugly. Let's try this one. JRRUV. Um, um, I keep thinking uvula here, but that doesn't work. Does it have to be in the right order? JRRUV. Huh. Anyway, I will pause, or if you want to try this one, pause the video. It's a good brain break. Get your brains out of physics for just a little bit here. And I'm going to show you the answers in 5, 4, 3, 2, 1, 0. It was uvula. Oh, they're not in the right order. Ah, no wonder. Second one, perjury, unique, bivouac. Holy cow, that's an unusual word. That's like an encampment for an army. Quartz, cantata, or rat-tat-tat. Is that a real word? Flummox, unknown, fjord. Wait, isn't fjord a Norwegian word, not English? I guess it's transferred into English. And a rainbow. Okay, that was a tough one. Normally at this point, I actually set up the two speakers in the room playing the exact same tone. And what happens on this one is as you walk around the room, you'll discover that where you stand, you can either find points of constructive or destructive interference. In this case, these lines represent crests or compressions of the longitudinal waves as they move outward, and in between here would be a trough or a rarefaction. If both waves are producing the same frequency, the wavelengths will be the same. And you'll end up with certain points that if you're standing right here in the room, or here, you get a crest from this speaker meeting up with a crest from this speaker all the time, and you end up with constructive interference. Also at this point, at this point, at this point, at this point, and at this point, and this point, these are points of constructive interference. There's another one here if I drew the other line all the way around. Whoops, somewhere over here as well. There's also some interesting points, though, where you end up with destructive interference. That is where a crest from one meets a trough from the other one. So, for example, right here is the crest of this speaker A, and it's right in between two crests from speaker B. So at this point right here, you would end up, if you were standing right here, you would hear almost no sound at all. The same thing here, the same thing here, 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 here. I don't want to draw all of them, but you get the idea. These are points of destructive interference. Now you might notice, hey, wait a second, Mr. Clymer, these seem to be along lines. Yeah, there are lines of destructive interference along these lines, constructive along these red circles, and if I continue down here, yeah, there's a point of destructive interference here as well, if I can draw all the lines in. There's lines of destructive interference here and here. Which means something interesting. I don't know if you've ever noticed this before, but every single speaker on the back of it where you connect the wires has a plus and minus. And you might say, well, why is that important? Do speakers not work, or do they make sound backwards if you hook them up wrong? No, but they're designed for this. If you hook them up correctly, plus to the plus side of the amplifier, negative to negative side of the amplifier for both speakers, you'll end up with a line of constructive interference right along this line. Typically, when you're watching TV in a home stereo system at home, you put your couch right in front of the TV set, which I'll draw right here. You want constructive interference to be right here at point C. What would happen if you hooked up one of these speakers backwards? You'd actually end up with destructive interference along this line, and you'd have to turn up the stereo really loud to be able to hear it. Meanwhile, somebody who's over here, say for example in the kitchen, would say, turn down the TV, it's too loud, because they're along a line of constructive interference if you hook them up wrong. Here's a nice simulation of that. This is actually, you can sort of see again the constructive and destructive. I love it here. You can actually see, I don't know if you can make it out here, these lines right here are where you don't hardly see anything at all. These are the lines of destructive interference between these two speakers, where you end up with the crest from one canceling out with the trough from the other. They're almost all dark. In between here are the points of constructive interference, where you're getting very large amplitude crests and troughs. I won't draw all of them in, but you get the idea. I'll do a few more over here as well. All right. Number 72 on your homework tonight, I wanted to do with you because it's a little bit complex. Yeah, it's a blue level problem. So let me quick read it to you. An object of mass m is connected to two rubber bands of length L, each under tension F as shown below. The object is displaced vertically by a small distance y. Assume the tension does not change, show the restoring force is that, and the system exhibits simple harmonic motion with an angular frequency of that. All right, so doing this one. First of all, we'll assume the restoring force is here. We need to break that into its vertical and horizontal components. Yes, I realize there's also a force over here. I guess I could draw it in real quick. That's going to be equal and opposite. What's going to happen to this horizontal component compared to that one? It's going to cancel out. So what I'm really interested in is just this vertical component of the force, which I'll call F sub y. This horizontal component is going to cancel out. This is my restoring force for the tension on one side, which they just label as F. Now here's the only ugly part. It turns out, and this is why I wanted to do this one with you, you might say, wait a second, shouldn't this be F sub x and not just F? In this case, they say that the tension, which would have been acting this way here, doesn't change as you move it upward, which I know is not realistic at all. So in this case, though, we're going to claim that this is still F over here. And don't ask me, it's the only way that this will solve correctly. So what do we end up with here? We've got two similar triangles. I don't know if you can see this triangle. The original triangle here, drawn on here, this is L, this is Y. That's similar to this triangle here, because this angle here is identical to this angle down here. And so what can I write? I can say the opposite side is to the adjacent side, Y is to L, as the opposite side, F sub Y, is the adjacent side, again, F. Rearranging that, I can solve for F sub Y is equal to that. What's the total restoring force? Well, technically it's twice that, because I also have the component over here acting downward. What's the negative sign for? The idea that if Y, if you displace it this way, oh, sorry, my pen's not drawing very well. If you displace it this direction, the restoring force is in the opposite direction. And there's two of them, one from each side here. So now the question is, does that fit that formula? Oops, sorry, I realized I drew over that spot. Remember, for simple harmonic motion to occur, Fs equal negative kx has to obey Hooke's law's equation. Well, plugging it in, my force is negative 2Fy over L equals negative k delta y. Y is my displacement. And sure enough, you end up with the spring constant is 2F over L. So now, how do I figure out the angular frequency? Well, first of all, let's figure out the frequency. If you remember, the frequency of a mass spring oscillator is 1 over 2 pi times k over m. That's the inverse of the period equation. Plugging in the spring constant from the one I have right here, it becomes this. And I end up with the frequency then is just equal to this expression here, which I admit is rather ugly. So how do I figure out the angular frequency? Well, remember angular frequency, omega, yes, it's the same as angular velocity, it has the same units, is equal to 2 pi times the frequency. So in this case, if I plug in the frequency from down here up here, I simply end up 2 pi's cancel, and I get omega is equal to this expression right here, which is the answer to the second part of this. Yes, I don't like the fact that you've got to assume that this side is f here, but it's the only way this one will solve. The rest of your homework and the worksheets are not too bad. I'm working on the answer keys for the worksheets this afternoon, and I should have them posted soon. Have a good night, and talk to you soon. Bye.